All right. Hey, everybody. It's Rob. If you're joining from the previous IoT, all the things, thanks for sticking around. If you're joining from previous episodes, thanks for coming back. This, of course, is AWS step functions. And today we're going to be talking about parallelism and concurrency in AWS step functions and AWS Lambda. Let me change the title here for y'all so that we get what we want. Hooray! We got the title. So here's what we're going to go over today real quick. Parallelism versus concurrency. Yes, they're two different things, but do we care in our context? And then I'm going to talk about three different methods of serverless implementation of parallelism to help you speed up the execution of your workflows. I'm going to talk you through when to use each with a specific use case. And I'm going to give you a built example of each. And it says build, but when I was pulling these together last night and building them, there's a lot of tempting of the demo powers. I'll be honest, I went ahead and deployed these before this to test them, and we're just going to walk through them this time. So the bright side is we know everything will work, and we can spend a little bit more time on the logistics or the specifics of it. So I'd encourage you to ask questions as we go, right? Like if you have a question just in general about parallelism or concurrency or all this stuff, please share them. There's a couple commands you can get in the chat. The links command that I just dropped in there will give you a lot of good links that we're going to cover today, including definitions of parallelism and concurrency, the definition of map state, JSON path, and all these different things that we'll cover. So that's there for your convenience. There's also a GitHub link and a docs link that you can use if you want those. So looking at our agenda here, the first thing we want to knock out is parallelism versus concurrency. And parallelism is executing the same task in multiple locations concurrently, right? And I should probably take out concurrency there. But what do we say? Let me check my notes. Parallelism is the simultaneous execution of possibly related computations. It's doing lots of things at once. Whereas concurrency is the composition of independently executing processes or dealing with lots of things at once. And I bring this up because some people, depending on which language paradigm you come from, you might understand one better than the other. If you're coming from something like Scala that implements true parallelism, then you can think about this like parallelism. But if you're coming from something like Go that thinks about concurrency as very different, you can think about this like concurrency as well. We're also going to get down into some of the language details of implementation, and then you'll see this stuff come back up. But the answer to that big question there from a serverless perspective is we don't really care. All that matters to us is we're taking big blocks of work and we're accomplishing them in a shorter amount of time by using more resources at the same time. So if you want to think of it as parallelism, that's great. That's probably more accurate. If you want to think of it as concurrency, that may be more accurate. Doesn't really matter to us. So the first, don't worry y'all, it's not all going to be slides. I really want to make sure I hit this because this is a little complicated. The first type of parallelism that we're going to talk about is parallel invocations. And this is almost like a default built-in when you're building on the AWS cloud. This is when you have multiple AWS step functions workflows or multiple AWS Lambda functions, multiple instances of them, or arguably even multiple instances of Fargate tasks running together. So whether you've auto-scaled them out or you've provisioned that amount of concurrency or whether it's just happening, it's the same definition executing at the same time with different inputs or different data. And so this can be thought of as like web requests that come in and are being processed through API gateway and are hitting a Lambda function behind it. All of those Lambda functions might be executing sort of staggered or concurrently, but that's that parallel invocation. The important characteristics to think about here are that each process is independent, right? So if I make a request to an API gateway and you make a request to the API gateway, a failure in my process has absolutely nothing to do with yours. So it shouldn't impact yours. It should be pretty much like an atomic transaction, right? And the example that we use here is if you have some sort of task that runs and looks for non-compliant resources, either scheduled or in response to rules, then it kicks off that remediation workflow for each individual violation, and the resolution of each individual violation doesn't have anything to do with the other violations. There may be one, there may be no others, there may be 1,000 executing concurrently, right? The limitation on parallel invocations is basically your account quotas, right? It's how many of these things can you execute at the same time. So there's, in the links that I just gave you here, I gave you both the step function service limits and the Lambda service limits. I'd encourage you to check those out. Most of them are soft limits. So if you're proving that you're close to running up against them, go ahead and fill a support request and ask for them to be increased. Someone will get with you and make sure we can get that resolved for you. But that's the limiting factor for parallel invocations. But it's really, it's a lot of independent little workflows doing their own thing at the same time, right? It's like, I don't even want to say ants because it's not a colony. They're just a bunch of individuals doing their own thing. So let's take a look at what this looks like in some code. When you look at parallel invocations, I've got a SAM template built here for us. And this SAM template comes from last week's episode of App 2025, which I'd really encourage you to check out as well. It's on Thursdays at the same time. What it does is it creates an event bridge, event bus, custom event bus, and a function for publishing events onto that bus, and a rule that listens for events and invokes a step functions workflow that's defined here, right? So your application is just putting whatever the event is. In this case, we use the expired subscription because that was already written. So anytime a subscription expires, that event is just put onto the bus, and this workflow is kicked off independently. And again, you go back to the example of like my subscription expiring yesterday doesn't have anything to do with your subscription expiring today, right? Maybe I've been a customer for 2 years, so I get a special offer. And then you were just on a trial subscription for 30 days, so you get an even more special offer. Who knows? But this is pretty straightforward, but I want to show you what it looks like visually. So when we come back over here and we look at parallel invocation, by definition, it's just a simple workflow, right? These things are for the one item that comes into the workflow, and then it's done. It doesn't look for all other canceled subscriptions or build statistics around it or try to process a batch of subscription expirations together. It just takes the one subscription in, processes it, and pushes it back out. So when we execute this, it's going to look like this. Oh, all right. So I've created a file here, and this will all be in the repo afterwards. It just has the format that you need for events to go onto Event Bus. And there's 5 here. 2 of them will trigger the rule, same as during the App 2025 episode. So when we put these events here, we'll get back. All right, none of them failed. That's great. That's what we hoped for. And then we get event IDs on the bus that you can use for tracing or debugging later, right? And we said only 2 of them would go through. But let's look at these events for a second. That execution will already be done, but we can tell that this matching event for this subscription really has nothing to do with this matching event for this subscription, right? They just happen to show up at the same time for our convenience of demonstration, and that's it. So when we look at these executions, we see that just now we had 2 successful ones, and if we dig into one, again, we'll only see the information about this event, right? The single subscription with its details. And then it completes by putting it back onto the event bus as a processed event, and we're done. So a lot of this, again, this functionality is sort of the default parallel invocation functionality that's provided to you when you choose AWS to run your workflows. This isn't necessarily something you need to engineer, although it is something that you should be thinking about, because you want to make sure that you have enough concurrency, that you don't get a backup here, that your cost is managed. Maybe these things are related. for one of the next use cases that we'll talk about, and maybe you could re-architect it and refactor it to execute more efficiently. So let's go back to our second type of parallelism, which is dynamic parallelism. Dynamic parallelism is also known as the map state in step functions workflows. And you choose this model whenever the workflow itself generates a collection of items, right? So if you're executing the workflow maybe on a scheduled basis, or you're executing the workflow in response to some request, but it needs to, part of that business process is identify all of the items that meet this condition and gather them, and then apply this task state or workflow to them, right? So the items are processed individually with an iterator that I'll show you, and then optionally reduced to an aggregate. And that aggregate can be, you know, any aggregate function, a sum, a statistical function, whatever it works out to be. The difference here, or one major difference here, is that errors in processing one item can typically affect the outcome and sometimes other items, right? Typically not that process on other items, but it can affect what happens at the end of the workflow. So I want to say hi to Nicolaus. Welcome to the channel. First time joining us. Appreciate you being here. We're discussing different ways that you can execute parallel workflows to speed up your workflows on AWS. So errors in one item when you're executing this way can especially affect the outcome of the workflow in aggregate. And so an example is an order fulfillment system. A customer places several different items into the cart, hits checkout, great. And you go out and you pre-authorize that payment, and then you need to pull and pack, right, before you charge. But say that you didn't have enough inventory to pull all of one item, you still want to ship the rest of the order, but you don't want to charge them for that. So the ultimate end of the workflow is the amount that you charge them, and it's impacted by a failure in one of your items that you've generated in your collection. This, if you also look at the links that we put in the chat here, I'm going to put them again for anyone new that's joined us. There is a step functions map state blog by one of my colleagues, Danilo, that uses this same example to walk you through the introduction of the map state. The main limitation around choosing dynamic parallelism is that your state in an AWS step functions workflow is limited to 32,768 characters. So that means that only whatever you can jam into that state can be used as an input or a result, right? This limits you typically on the order of like hundreds of items if you're designing it well, maybe thousands of items if you're extremely efficient with it, but you're kind of running out of space there. So you need to be judicious with what you're putting in here. And there's also a different set of limits on how many of these will execute concurrently. So you'll want to check those service limits again. But I want to go back now and show you what this kind of code looks like. So we'll close our parallel invocations example, and we have dynamic parallelism here. This is a workflow that I've generated with the AWS toolkit for Visual Studio Code. And one good thing about this, the way I generated it was by creating a state machine, if you haven't been with us in previous ones, and then choosing map state here. So it's one of these quick starts that'll get us going, okay? I'm not gonna go back through that, but we also get the visualization of this workflow over here. And you see, just like we were talking about, customer places an order, and we say, okay, let's authorize that charge. And in this case, we just mocked this up with a pass state, and we've said, okay, the total amount of items in their cart plus shipping and tax is 81.48. Let's authorize that. The authorization succeeded. Great, let's move on. We check this authorization here, and we have a choice. Did the authorization succeed? Yes. Retrieve the items. No. Go down here to failed. And again, all this code is going to be posted to the repo afterwards, so you have a working sample. We retrieve the items using a pass state just to generate this collection, right? So we have this collection of 2 items. And I have something bouncing in my dock that's very strange to see on screen. We have this collection of 2 items, and that's the collection that the map state is going to iterate over. So you see we placed this collection into the order items path in the JSON path. And then in the map state, our items path is the same, right? Now, this is really important to note. Again, I've left you a link to the JSON path definition in the links in the chat. We're going to do an episode next week, I believe it is, just on JSON path, on input path, items path, result path, output path, all this stuff, right? Because it helps you track the state as it moves through. So then we've provided this max concurrency here, which means for all of these items, if you see this dash line box over here with the sort of parallel floating look to it, for this iterator, it means we're going to execute at max 40 concurrently. And then as they complete, an iterator becomes available to execute the next one. Then just like any state, when we're done with this entire iterator, we'll move on to the print label phase. And so here we've just mocked up these, lock the item, pull the item, pack the item. And then you print the label and you complete the charge. So this complete charge step can be the Lambda function that takes in the items that were actually packed and then only charges you for those. Each item, as you're processing through it, when you try to lock, if you fail, you can put a separate workflow in there. And if it can't be locked, then you push it into a delayed items queue for later, or out of stock items queue for later processing. All these types of things can grow out of here, right? But I just wanted to give you this most basic workflow that we have. And so this one we can invoke directly here from Visual Studio Code using dynamic parallelism. We'll start execution. Oops. And because we hard-coded everything with pass states here, we don't really need any data to pass to it. So now we go back to our state machines here. We have this dynamic parallelism state machine, and we see that it just succeeded. And this is in the AWS Management Console under step functions. So if any of this is unfamiliar to you, please let me know. I'm looking at questions. I don't see any that have come up, but I am paying attention. So if you have any, let me know. And we see the same definition that we had before. What's interesting is to track the change when we move into that dynamic parallelism state or that map state. So we get to here, the output is as we expect, right? We've got this order items state, 2 items in a collection that we're going to pass in, and that's where our iterator is going to pull its items. So now if you look, we can highlight this entire collection, which shows us the statuses of, you can filter here based on whether an iteration succeeded or to only see the ones that you want, or you can filter based on specific indices from that items path that you gave it. Or when you go into an individual step inside that workflow, then you can move back and forth between those values. So we'll see here, this was our first line item that we took 1 at 250. And this was our second line item where we took 17 at 421, right? So you can really granularly see what's happening inside this state, even though you're doing multiple things at the same time. And then we see at the very end of this, we get this confirmation that we sent back, 1 for each item that they were locked, right? And of course, in a real workflow, you're going to want to build this out where this locked items includes the SKU or some sort of line item identifier or whatever your business process is. But you see that we have 1 entry here for each of these items. So we could now take, at this complete charge step, we could take this locked items as input, and we could perform that reduce operation on it to determine what the total cost is that should be charged, and then complete that charge, right? Any questions on that? Looks like we're tracking. All right. So again, that's dynamic parallelism, or the map state. And then now I'm going to show you the third category, as promised earlier, is function native concurrency or parallelism. And either term applies here based on whatever your language has as its paradigm. So you do this whenever a single task in your workflow receives a single input, and that task is generating the collection, performing the operations, performing the reduction or the reducing operation, and returning that reduced result, right? So what do we mean by this? An example is like traversing an S3 bucket in prefix, looking for items that match a pattern, whether it's upload date time or media type or file name or size or whatever you have, right? Or permissions, any aspect that you can query, you're essentially checking that bucket. So the input is an S3 bucket and a prefix, and the output is the number of items or a collection of items or a DynamoDB table that contains information about the items that met your function. Importantly here, errors in one item can impact the entire task, sometimes even to the point that the entire task fails to complete, right? So super awesome info. Thanks, says Majestic Pears. Thank you for being here and for the compliment. I'm happy to put it out to you. Again, if you have questions, please raise them. I want to get them answered for you. But errors in one item as you're working through can impact the entire execution of the task. Maybe it's an all or none type task, right? So it's even more tightly bound than using dynamic parallelism. Your main limitations on using this type of concurrency or parallelism are just the limitations around execution in the AWS Lambda runtime environments. So your functions can't execute for more than 15 minutes. If you can't get your workflow completed in that, or your task completed in that time, then it won't work for you. Whereas you might be able to do that with standard workflows in AWS step functions, which can run for up to a year. Your limitations on memory at 3 gigabytes is the max. So if you can't fit all of your processing inside 3 gigabytes, that won't work for you. Disk space, things like that, right? So you have to be able to execute this inside your language's runtime. Also, if your language isn't very good at parallelism or is sort of awkward, or concurrency, or sort of awkward around it, then you may not want to do that as well, right? But that's more, it's the word that I'm looking for here. Those are more like personal concerns and how you feel about the runtime. So let me jump in here and show you what this looks like in code. It's very similar to our parallel invocation, and in fact, these could be used together, right? You could have a parallel invocation of tasks that the task generates a collection of items and performs a reducing operation on it. You could use all three together, where you have all these workflows coming in, and part of the workflow is the workflow generates the long-running set of the collection of items, and then individual tasks operate on the item. So all of these things are here for you. As I get into this, Majestic Pairs, how would you handle multiple error handling paths? What if each customer wants errors handled differently? I'm not sure I understand what you mean by customer here. If you mean consumer, like each executor on the item. Oh, you're probably referring back to the example of the e-commerce, right? Where we talked about placing an order in a cart and executing the order. Multiple error handling paths will be the subject of a future episode. I'm not just kicking that down the road for you, but there's a lot of it depends around that. I would say it depends, and you'll handle them differently in each paradigm that we've discussed here. So when you look at the parallel invocations, you're handling that error in a more simple fashion. You can use retry logic that's built into AWS step functions, but you sort of only have the one error at a time, so it's a little easier to reason about. Quick side note here, I really recommend that you throw all of your errors out of your code up into AWS step functions so that it can handle that retry logic for you. That's a better practice. Make your functions simpler and simpler and simpler, right? Rather than rewriting that type of code. if you're doing dynamic parallelism in map state, it really depends. So you can reassemble those errors at the end, and it depends on how you define an error. Like, is an item being out of stock an error, or is handling it, putting it into the out of stock queue and returning success? I would argue it's success, just of a different kind. So again, a lot of this is an it depends answer. Finally, the function native concurrency, I would recommend that you handle it in accordance with your language's error handling paradigm. After that consideration, that I would still throw it back out to the step function to handle. If each customer wants errors handled differently, that's where you talk about composition of workflows. And I would say that you can create individual workflows for each of those types of customer wants, and you can route them based on fields there. So, okay, answered your question. Thanks. Good. So function native concurrency. The example that I've got here is, again, an example that I've used in the App 2025 program. The things we need to look at here are our step function and also this do stuff function. For this, I've written it in Go. Go is known for its concurrency. It's a simple implementation of our example. We define an input type for our Lambda function. That's that S3 bucket and prefix. The simple ops in our output is just going to be the number of operations performed. And then our handler gets us a new S3 object, lists them. This is not production, y'all. I do not handle pagination. If you have more than 1,000 items with the V2 list objects, you're still going to have to handle pagination. I don't do that here because I pre-rigged the data. This is a very simplistic example. But so we list all the objects that satisfy these criteria. Check for errors as always. And then this is our language-specific concurrency, right? If you're not familiar with Go, it just essentially creates a wait group, and for each thing that matches our pattern, we kick off a Go routine, which is a lightweight function. First, we say, hey, we got one task to complete. We initiate that task. That task finishes. We call it done, so it removes one from the queue or from the counter. And then down here, we just wait for the counter to reach 0, and it reaches 0. And we create our return object and pass it back, right? So this one, I've created a file and populated some data for us. This test data just passes in a bucket that I've created in the stack and a prefix. What I did was I put 400 objects in the root of that bucket. I put 400 objects inside this Rob Stuff folder in the bucket. And so whenever we list all of these items, we should only list the ones that are inside the prefix. So the number of operations performed should be 400, right? So again, function native, start the execution. I've got that sample file that we just gave it. That was test data, right? I believe. Yeah, perfect. And we execute it, and we'll return to the AWS management console over here for a look at this state machine. So this one, yeah, I had some errors earlier. You know, this is why I don't tempt the demo spirits. We come over here and we see we just had this simplistic do stuff workflow that we built, and it did stuff. It took the input that we gave it, the bucket and the prefix, it passed it in, and it returned this payload, operations performed 400. So you can see this is a very simple, you don't get the idea that anything parallel is happening here. And in some cases, you may not even know, right? I just say, here's an S3 bucket and a prefix, go do some magic. That magic could be some sort of big data processing that reads all the objects underneath that prefix, and, you know, I don't know what's there, but you've black boxed that function for me so that it's opaque. And then it returns a magic number back to you. The point is, you can't really tell from here that anything parallel is going on because it's going on inside this single invocation. So that's our function native invocation. And that's it. Hello, Kay Bensden. You're showing up right when I finish everything. This has been an unusually short episode at 30 minutes. I could go over the whole thing again if you want, just like a little private episode. Any questions on the ones that we've covered? Again, those three patterns were parallel invocations, dynamic parallelism or the map state, and function native concurrency. The three examples we used were scheduled tasks that identify resources that are independent for remediation, a checkout or order fulfillment system that checks individual items and then charges you for the ones that ship and puts the ones that don't ship into a queue, and an S3 bucket and a prefix that performs some sort of operation over all of the objects in that prefix and returns some sort of aggregate value. Again, for the links, I'll drop these in here one last time for those of you that have made it. For the GitHub repo, it's here. I haven't put these up yet. I'm going to clean them up, make sure there's no like weird data in there that would cause you to not be able to deploy it in your account, and I'll push it up. The other thing I would suggest is on Thursdays, if you're interested in building more with these types of services like Amazon Event Bridge and AWS Step Functions, Amazon SNS, Amazon SQS, join me on Thursdays at the same time for App 2025. We're going over how to architect an entire application with very little code. It's not no code, but it's service integration heavy. So these things are very resilient because the underlying, APIs don't really change. You don't have issues with dependencies, with operating system patching, all of this stuff. It's like sort of next level serverless. So I really suggest you join for that. The link there is to my Twitch channel. It's also twitch.tv/Rob Sutter. I don't see any comments in the chat. I'm happy to stick around. If you have any, I'll be here for a little while. I'm going to go ahead and end the stream here. I do want to say thank you to everybody for joining today. Again, you got my my Twitch channel up there, /Rob Sutter, twitch.tv/Rob Sutter or robsutter.tv. My Twitter is there. If you have questions, feel free to DM me. My DMs are open. It can take me a day usually to figure out that somebody who I don't follow has sent me a DM, so be patient, but I do respond. And again, I just want to thank you all for joining us. Thanks to my colleagues who are in here moderating. What happens if an error occurs within a parallel task in a step function? From Bogard. Yeah, so you can implement an error handling workflow specific for that inside the iterator, or you can place it back into the state and handle it outside of there. It depends on how you define an error. So in the example that we had, we talked about if an item in an order has gone out of stock between when you said send the order and when we started fulfilling it, is that an error? It's not ideal, but it's up to you and your business process to determine if it's an error. I would not call that an error in the workflow. I would say it's a branch in the business process. And so I would kick it off to the branch. Now, if you have an execution error, like you got bad code into there, calling a Lambda function, it failed to execute, things like that, that's when you would want to use robust error handling inside your step functions workflow to catch those and then either retry or send them to a queue. But you definitely want to explicitly manage for those. That's part of my recommendation on sending it back out. Where you put that largely depends on, does that error impact the collection of items that you're iterating over, or does that error impact only that item, right? So can you handle the error inside the workflow and go on with your life and return some sort of result, or do you need to error the entire iterator? That's something we'll cover in a future session, but there's a lot of detail to dig into there. So thanks for that question. I can't read your username, Holly F UK. Thank you. Thanks for joining us. I'm going to end the stream here. I'm going to stick around. If you have any questions, please keep them here. I'm still here in the channel chatting. Thank you again for joining us, and I hope you'll join us next week and join me in my channel on Thursday at the same time for App 2025. We'll be covering standard workflows and the callback pattern for placing human interactions into your step functions standard workflows. Thanks, everybody.